couple of changes in the talk by Monique, and after Felipe's talk. And also in the afternoon, I know that's really intriguing, the program, and many of you are leaving, but we decided to have a discussion on what is beyond W0 WA, because I think this is something we should discuss. You know, I know people want to break on the CDM, but then we have to think what's next. So, and there are a lot of things. So this will be led by Vivian Miranda and Diogo and João. So this is a three, of course, only if you're interested, if you want to come. Okay, so now we're going to have Felipe Falciano from CBPF, and he's going to talk about gravitational waves and early universe physics.
Thanks, Roger. So, morning, everyone. You know, it's the last day, so let's start slowly. So, I'm going to talk about gravitational waves in the early universe, but this is basically like the first part of my talk. I want to make like an invitation to work in the early universe. I think there's a lot of nice things to do in the early universe. And the second part, I'm going to talk about specific work, very recent that I did with some colleagues, and show how we can constrain the physics of the early universe using data. Okay, so you all know a lot about gravitational waves. We have like indirect evidence since the 70s. We have direct measurement from LIGO since the 2015, 16. And we know that gravitational waves would be awesome from multi-messenger astronomy. And these two evidence comes from astrophysics, basically. And we have also PTA. Gabriela gave a very nice talk for us, explaining a lot on how PTA can be used to like supermassive black holes. It's a very reasonable assumption to source the signal of PTA. So you have strong evidence for PTA. Here you have the curve, like the having down curve. This is basically geometry, right? So this is showing us that the signal, it's a strong evidence, but let's say it is a signal, okay? And this shows that we are very confident that this has to be like a stochastic background, okay? So supermassive black holes, we know that black holes exist. We know that supermassive black holes exist. So it's very reasonable that supermassive black holes is the source for this kind of signal. But as Gabriela said, there's the slope of the spectrum that's not fitting. There's the amplitude issue. There's a lot of issues. Could be just a source of noise. But for me, this is very interesting because I know that the supermassive black hole signal has to be there, but maybe it's not all the story. So maybe there's also like a signal from the early universe in the stochastic background. So there's this paper. I think Gabriela also mentioned this paper from the Nanograv collaboration. So what they analyzed is, okay, what if it's not supermassive black holes, right? And they made a statistic and calculate the Bayes factor. And you see, also there's a lot of things. I don't know why they call new physics, because some of them, okay, you have cosmic strings. This could be called new physics, but gravitational waves is not new physics, but they call new physics. Okay, inflation for me is not new physics, but okay, they have the right thing. So, and you see that, for instance, scalar induced gravitational waves has a huge Bayes factor compared to supermassive black holes. Okay, so it's very soon to say anything, like Gabriela was saying. Could be just noise, but maybe we'll have some early universe signal inside the PTA. Okay, and okay, so just to give flavors, this is scalar induced. I'm going to talk about this kind of effect, like Gonzalo said yesterday also. So inflation is not that bad, right? So below 1 means that supermassive black holes have a higher Bayes factor than the model. So everything above 1 means that it's better than supermassive black holes to fit the data up to date, right? Okay,
So in that diagram, you distinguish between the possibility of being primordial?
yes, yes. Almost all these possibilities are primordial, like domain wall, strings, scalar induced, inflation. All these are, maybe that's why they call them physics. All these are primordial. This is just a motivation. Okay, so yeah, let's see if there's nice things in the universe. That's basically the idea. I'm not claiming that this is the answer. Okay, so you heard a lot of what to do with gravitational waves in the late time universe. I'm going to focus on early universe. Okay, so there's high energy physics, a lot of nice things to do with high energy physics, primordial black holes, and tests like models of beyond standard models also of particle physics. All this has to give signals in the leave signals in the gravitational wave, in the gravitational stochastic background gravitational wave signals from the universe. So you can use this to test your models. Okay, so early universe. Maybe I'll go faster in this part. Okay, so Gonzalo yesterday explained a lot of how inflation works. Just to give you another way of describing the same thing. So he's shown a plot that's basically this one, but was going up in time, but it's the same thing. So here you have inflation working. So this is conformal coordinates. So inflation is this part. So we have like a exponential expansion, and this because I'm plotting h to the -1. So basically this is inflation, and here you have like normal expansion, like a radiation era, matter era, whatever. Okay, so inflation, that's what inflation does. So you have like nowadays sub-horizon modes. That was super horizon back there during the CMB. But what inflation does, it put inside the horizon again. Okay, so you put initial conditions here and evolve the system. Okay, so you have like the normal single field. You have this slow roll parameters that can be associated with the potentials. And it's so what you do is like you run the machinery. You see that if you look for just the scalar modes, you see that even though you have matter and gravity, at the end you have only 1 degree of freedom, a scalar degree of freedom, looking for the perturbations, right? And so it's basically the Mukhanov-Savaki variable. And you can see that working all the equations, it satisfies this kind of equation. So it's a very simple equation for each mole K. It's basically just a harmonic oscillator with a time-dependent mass. So this Z double prime of Z works as a time-dependent mass. So you can quantize the system. So just quantize your variable, give an adequate initial condition. So let's say Bunch-Davis vacuum, and you can work out what you should see in the CMB, right? And you have like this kind of parameterization. You have the amplitude, the spectral index, and you can relate these guys to the slow roll paradigm. Okay, this is like common thing. And if you look for gravitational waves, it's almost the same thing. It's very similar actually. So you start with your metric, you perturb, you expand your action up to the second order. That looks something like this in the traceless, transverse traceless coordinates. And okay, so and if you expand your tensor modes using the polarization, you actually end up with an action that is very similar to scalar mode. Okay, so everything works very similar to the scalar modes. And you have almost the same equation, and you can also fit use this parameterization, the amplitude and T, And this R is basically one of the things that Planck constrains, right? And using single field, slow roll single field, all these are connected with the slow roll parameters. Okay. Yeah. So the Planck has shown that NS, it's very close to 1, 0.96. And this R, that's basically the ratio between tensor and scalar modes. It's very slow, right? This means that you should not have like significant gravitational waves in the early universe. So what I'm talking about here? So what the hell? So we know that Planck showed that it should not have a gravitational waves. But Planck is very constraining, but in a very limited range in K, right? So we know a lot, but only in this range. And I just wanted to point out, this is basically the R against an S plot. You see that some models are off, but this yellow one here is no, it doesn't work. So the yellow is basically the alpha attractors, the model I'm going to study. And you see that varying the parameter, that's basically alpha, you can go up to here in the middle. So it's a very good fit of Planck, okay, the alpha attractor. Okay, that's so what the hell, right? So why I'm talking about early universal gravitational wave. So the thing is that CMB is very constraining, but in a very limited range. So we don't know anything about what happens here in higher K, right? So you can have this kind of power law that fits well the CMB and then have a huge bump. Gonzalo showed us examples yesterday also. And the interesting thing is that these bumps can get into like a future surveys, like LISA, Einstein telescope, and stuff like that. So what I'm going to show you today is we analyze a specific model, hybrid alpha attractor model, and we use large-scale structure constraints, CMB, mu distortion, to constrain the model. And I want to convince you all that nowadays it's very constraining already. Okay? So you cannot just make a model of early universe without constraining. Okay. Okay, so I'm interested in trying to understand the physics of the early universe. So one thing that is important is to see what is the typical frequency and which survey is going to be the best to study a specific like a high energy model, something like this. Okay, so you have to relate the frequency that we measure today with the frequency when the gravitational wave was produced, right? So basically, this you have just redshift, but be careful. When you redshift, your scale factor is not, the scale factor doesn't go like 1 of t, because in the early universe you have a lot of pair productions, right? So every time you have like freeze out of some of the particles, you inject energy back to the medium, right? So the temperature doesn't go with one of the scale factors, okay? So at the end, so you can rewrite this in terms of the effective number of degrees of freedom, or in terms of and also with the effective number of degrees of freedom in entropy. And you end up with a Hubble expression like this. And if you do it correctly, you can associate your frequency with the frequency when the gravitational wave was produced by this relation, okay? So let's try to work a little bit better this F star. So let's say that you produce a gravitational wave that has this reduced wavelength. It's just the wavelength divided by 2pi, right? So we are interested in cosmological mechanism, right? So this should be something of the order of the Hubble radius, right? So let's put our beginners in this small epsilon star here. So you can relate the frequency with the Hubble factor, and you can rewrite the frequency today in this way. It's just putting the numbers, and you can build this kind of tables, right? So if you want, and here is just a map of frequency today. So you have the surveys and what kind of the energy of the mechanism should have been in the early universe. So for PTA, you're looking for like something that it's energy of 0.1 GeV. These you can measure something of like 1,000 GeVs. And for Einstein telescope or LVK, you have like things like 10 to the 9 GeV. So it's very huge energy, much above our standard model, right? So using gravitational waves, you really can study the very high energy physics, right? And you can ask like dark matter freeze outs, see if you have transition in electroweak phase transition, if what happened, if you are beyond standard model, what happened, because okay, so standard model in probably shouldn't give like a very strong signal of gravitational waves, because these two phase transitions are, the QCD is crossover and the electroweak it's not significant, but there's a lot of models beyond standard model that you can produce like significant gravitational waves. Okay. Okay, and so there's a lot of possible mechanisms to produce gravitational waves in the early universe. I'm just like naming a few. So every time you have like particle productions, you're going to have like anisotropic stress, and we know that anisotropic stress is source for gravitational waves. So this is one kind of a possible way of producing gravitational waves. Modified gravity, there's a lot of things. I'm interested in this too, actually, nowadays. So I'm going to talk about that scaling-induced gravitational waves. And like Gonzalo said yesterday, this is very linked to primordial black holes. And also now I'm very interested also in first order phase transitions. And just another thing that I think it's very interesting in gravitational waves in the early universe is that you're going beyond CMB, right? Yeah, with gravitational waves. And you have to propagate what happened there to today. So you have this transient function. So the signal of gravitational wave is sensitive to how the universe expanded before CMB. So you can only see this kind of things with gravitational waves. There's no way to do it with anything coming from CMD or whatever. So the signal is also sensitive to the expansion history. So I'm not going to, I'll probably skip this discussion on, I can discuss later if anybody is interested in first order phase transition. There's three contributions, but okay. Okay, so let's, before getting to the model, so let's formalize a little bit the scaling-induced gravitational wave, how we proceed. So imagine that you have like your metric perturbed. So you have like the scalar perturbations. This is first order. And I'm considering that I have a tensor perturbation that is only second order. Okay, so I'm not considering H. This H here is already second order. I'm assuming that like inflation, linear perturbation is completely negligible to the tensor modes. Okay, it's a chance. Let's see. Like yeah. Okay. So and if you work out the equations, then the evolution of the tensor perturbation is something like this. So you have the source, you have the projector, doesn't matter, but the source is basically the scalar square. Okay. So it's the scalar mode square. It's just you go just to second order perturbation and you see this. And you can you can calculate this omega GW. And it's basically depends on this quantity. And this one, it's a double integral, doesn't matter, has this function here, doesn't matter. The important thing is that it appears the scalar power spectrum squared. So the scalar induced gravitational wave that we expect to measure, it's something that it's 10 to minus 6, let's say, order of magnitude, 10 to minus 6, the scalar power spectrum is squared. So if it's the same B, this is a very small number, right? So the only way you can have a scalar induced gravitational wave is you have like that huge bump or large case. Otherwise, you won't get anything. That's for sure.
Can you explain to me why you only have quadratic terms in the first order potentials and not potentials at second order in your source? Second order potentials,
You mean scalars?
yeah. Or second order, second, the square of vectors, or I don't know.
Why I have only squares of 5?
Yes, and
Because anything that will be second order scalar will be at least third order here.
you could have one field to second order.
It doesn't appear alone.
Why?
scalar.
There's some magical symmetry that.
Magical? No, I think it's magic. Let me see.
Because-
Well, if you work out, there's the there.
Yeah,
Okay,
but
so
why, so let me ask a different question. Why didn't you expand your magnitude to second order perturbations?
because that's the signal I want to see. Okay, so in first order they are decoupled, right?
Right.
So at second order everybody's coupled.
Right.
Okay, so I'm looking for a specific, so I could have here like vector perturbations, squared also, stuff like that. I'm assuming that they are connectable and the tensor perturbation first order are negligible also. So the only thing that survives is first order scalar and second order tensor. So your question is, how come I don't have like a second order scalar
Yes,
term here?
yes.
Because it will only appear at least at third order. So you won't appear like alone. Will be multiplied at least for something of third order, first order. So if I can remember it, yeah.
I was just going to ask if this mechanism could also generate a second order vector perturbation.
Yes.
Are they negligible? You are just assuming they're small, or can one show that they doesn't take much value?
No, you have to work the fit. I don't know. Yeah, yeah, but you could have. This way you could have. Okay, so I don't have like
It's very technical. Okay.
no, it is not. I forgot. There's a very easy way to see that it's going to appear, it won't appear alone, but I forgot. I can show you later. And one point that I would like to stress with this plot is just is that be careful, because even though you're looking, you're like everybody does the thing, so you don't have problem with large scale structure, but even and I'll come back to this later. But the slow roll approximation is very bad in this kind of models. Okay, so you have to take care of this. So don't ever trust slow roll approximation. This is what it's being shown here.
But don't you have the super slow roll? Because
The ultra slow roll, yes.
ultra slow roll.
You can still have, yeah, ultra slow roll, you have this kind, actually, this is an ultra slow roll. It's a model for ultra slow roll.
So it should be a very good approximation.
No, no, because the epsilon is very small, but eta is not small anymore. So the slow roll approximation breaks for ultra slow roll. Okay, and like Gonzalo said yesterday, so this kind of effects, like a huge bump in the scale spectrum for a large case, normally comes with a lot of production of primordial black holes. Okay, so it is very constraining. Like you cannot do much with primordial black holes. Like if you try to there's just a few windows that. This is a mass, right? You look in the top, you have the masses. So there's a few windows for primordial black holes, and specifically to have like the explain the whole dark matter with primordial black holes is very difficult. You have only this D and A window. But even my point here is that even though it's very difficult to have primordial black holes as the whole thing of dark matter, I'll argue the opposite. Like really be careful with production of primordial black holes. Like you always have to test if your model is overproducing or not. I'm going to show this.
Okay, so just because it's not really fair to say that the median masses are larger than expected. What is really strange is the bump in the spectrum. But nobody knew what to expect actually.
You mean between 10 and 50?
Yes, I mean the
Okay.
fact that there is a bump and not a smooth power law, that's strange.
Okay, okay.
But the absolute number, I mean,
Yeah, I'm
it's
here-
huge uncertain. So
Okay, fair enough. Here's just like a sociological slide, maybe saying why the interest in primordial black holes came up again. So this is like a lot of people thought, oh, okay, so we didn't expect this. Let's look for primordial black holes. But from the
But the-
physical point of view, I agree. Okay,
the
so
expectation range is for, I mean,
But-
at the range of few order of magnitude. So
okay, but the pair stability is an issue.
no, the pair stabilization, but it's only one event. So
Okay,
pair stabilization.
fair enough.
So you mentioned then that these bumps in the power spectrum can generate both primordial black holes and scale-induced gravitational waves. So what is the range of compatibility between the constraints that you already have for both? Like primordial black holes will define one region of possibility, but I imagine that the scalar-induced might have maybe a different possibility.
Yeah,
Are these compatible?
So we don't have data for this yet, right? So we're gonna have for Lisa, but for now, we don't have data for the gravitational waves in the early universe.
So you have
Maybe
freedom
PTA,
to-
maybe PTA will help us. So one thing that I really want to do, and that's how I'm going to end, is like say, okay, now I know how to constrain the physics of the early universe. Then now let's try to model this with PTA data. That's my, I haven't
You have
done.
the freedom in the PTA side.
Yeah,
To
yeah.
adjust the.
Yeah, or Lisa. Lisa will help us. And maybe I said this, I don't. Okay, so let's focus on this specific model. There's a lot of tricky issues here. So I'm going to focus on this hybrid alpha tractor model. Okay. And it's a very, very new paper. It's not published yet, but it's already in archive. I did this with Luis Felipe that's here, Michael, and it's my PhD student at UFIS, and Laura Iaconi is in London now, and Queen's Mary, I think, right, Luis? Queen's Mary. Okay, so what we are looking at here? So the whole thing is that we started studying, we just wanted to see, okay, let's see how much gravitational wave we produce, let's see how fun it is, how much physics we can do with this. And then we started to understand that, oh, things are much different than we thought. So there's a lot of constraining powers in large scale structure, okay? So we came up with like, okay, so we think that this is a nice way to proceed. So a few steps. So we have to calibrate what I'm calling here, calibrate horizon crossing of scales, right? So you have a model, so you have to really take care of how, when you're like a large scale structure like CMBK cross the horizon, you have to control all this. Then you put constraint from large scale structure, basically CMB and new distortion. And then you have this, what we are calling theoretical checks. You can say like overproduction of primordial black holes, let's say. And then we can look for the small scale phenomenology. That means primordial black holes and scalar-induced gravitational waves. Okay, and try to see if you can see this kind of signals in the future. Okay, so the model, it's a very nice model. It's you have inspiration in supergravity theory. There's a nice paper from Renata and Lind. You can look, there's that picture over there. They connect this with the Poincare circle. But for us here, the main issue is that this kind of model has a non-canonical kinetic term. Okay, so you have this two Here I have only one field, but I'll have two in a second. So this phi field here has a non-kinetical term, right? But you can turn this kinetic term canonical, just make a change of variables, right? No issue at all. So the thing is that when you have this kind of model, you can change variables and you get a hyperbolic tangent in the potential. Basically, it's this, okay? I'm not going to details of all these theoretical issues connected to this. Okay, so this is alpha tractor.
So it's a scalar field with some potential. That's
Yeah,
like a quintessence model. Let's say.
Isn't
Like,
this equivalent like K inflation, like?
not exactly K inflation. Because you have a non-canonical for inflation.
Yes.
Yeah, but I think it's more subtle. And
So is there a problem in your model when phi is the
it's finite, yeah, it cannot, yeah, so it's exactly, so this goes to infinity when phi, yeah. So you're limited in a finite region for the phi, the cursed phi. But when you go to the capital phi, like normal phi, it goes to infinity. Okay, so that's how it has this kind of interpretation, Poincaré, this. Okay, so when you look to this picture, it seems that the angels and devils are decreasing in size. So you have an infinite number of these figures, but actually they are of the same size. Okay, so it's just a matter of your coordinates. Yeah, there's a geometric interpretation of this. But so single fields are very nice to fit the data, like I said. Like you have this, the alpha is basically the curvature or the size of this disk. So you can really fit very well the data with alpha tractors models. But multi-field alpha tractors are not that good for fitting the data. You have the issues. And for me, the problem is that the single field alpha tractor doesn't give all these nice features of a bump in the scalar spectrum. Multi-field does, but has problems with the data. So we cannot work with this too. Okay, so what to do? So we go to this hybrid alpha tractor. So just the hybrid inflation. Well, yes.
What are the problems that those models face today?
No. It's fitting DNS, the scalar aspect doesn't fit well. So hybrid inflation will be a potential like this. So we have two fields, right? So it's multi-field inflation, but just two. And what we do is, we are not the first one to do. There's Matteo Braglia has a very nice paper on this. So to go to a hybrid alpha tractor, you basically change, this is the potential, so you change the kinetic term, right? So you can have, for instance, the phi has a non-trivial kinetic term. The price to pay is that when you canonize this, I don't know how to say it, so to make it canonical, what you get is a hyperbolic tangent in the potential. Okay, so you can think that it's two fields with this kind of potential, and that's okay. Okay, it's a way of understanding this model. So let's see
Sorry, is something here,
yeah.
the canonical term here is alpha factor for one of the fields.
Exactly, and this is important. It's just for the phi, not for the chi. And okay, so and this is important because see this. So we have this potential. It's very good too. So the potential is plot here. So you have phi and chi, and so the system when it starts very here. So when the systems start, you give initial conditions here. So the potential is very steep for chi. So at the beginning, chi goes to 0 very fast. And then you start the alpha tractor phase and everything is done. So here you have the alpha tractor and the CMB mode cross horizon exactly during this phase. So it's everything's safe and works perfectly well for fitting the data. And afterwards, you have this turning and you have another phase here. And here you have the bump of the. So if I change and put the non-canonical term in the chi field, then the CMB scale is going to cross, not in the alpha vector phase. I don't know what happens. Maybe it's a nice thing to check, but. Yes, so that's mainly the dynamic of the model. I can give more details afterwards, but the main issue, the main points that if you look for the effective mass of the chi field during this phase, he's very close to zero, right? So the effective mass of the chi, it's something like this, and the phi is evolving, so it is positive for large phi, but at a specific critical value, the mass becomes tachyonic, and then this guy moves away from zero. That's the idea. So it's very, very easy to understand what's happening here. Okay.
You have isocurvature modes because this isocurvature perturbations.
Yes, but it's transferred to the back at the end. So you produce isocurvature, but at the end you transfer everything to adiabatic. Okay, so in the CMB you won't see adiabatic mode. It's good that Lily's over there is like, yes. So I'm safe. I'm not saying anything stupid. Okay. So let's try to constrain the model. So this model has a lot of parameters you can see. So there's D. So we have D, G tilde, M tilde, chi naught, and M and capital M. Okay.
So D does not appear in your.
No, yes, I want I wanted to skip this. Yeah, you're
There's
right.
no D there.
Yes, that is to fix some of the issues of hybrid models. I didn't want to get into the back. If you don't put this D, you can have like eternal inflation, and it can produce topological defects if I'm not wrong. So this is the very potential to fix some of the hybrid models.
A linear term in potential is kind of strange.
Yes, and there's some subtleties that I'm not going into here, but you have to sum a constant to avoid the cosmological problem at the end. So yeah, you're right. But this D is very small, but yeah, it's a subtle.
It's dimensionful. It
It's
has some dimensions, right? It's dimension energy cubed.
no, I'm over here. So M has an M. Yeah, I think it's dimensionless.
But no.
All these are dimensionless because I put it the M squared.
But even with M square, you have a chi, which has dimension energy first, so D has dimension of energy.
No. Things are fit to all these parameters are dimensionless, right? I think so.
Oh, just count dimensions, right? So there's dimension 2 in the mass, dimension 1 in the field chi, and the potential has to have dimension 4. So D has to have dimension 1.
Dimension -1 there.
Minus one.
Why minus?
Yeah, have M squared.
No,
I
it's
mean,
1.
chi is canonical normalized, right?
Chi is kind
That is normalized, yes.
Then D is a mass.
Yeah, this mass, it's
Yes,
energy.
nice.
It's not dimensionless. So when I say small, no, there's
Compared to plasma, yeah.
there's dimensions there.
Yeah. Yeah, but it is, yeah, you're right. But I didn't mention because, yeah, it's just small thing. But you're right. Okay, but my point here is not, I'm not advocating for this model. I'm advocating more to how to proceed, like how to treat early universe models. Okay, so I'm not going to defend this kind of model, just what to do, basically. Okay, so in fact, you have a lot of parameters, so it's not a good model to try to fit anything, trying to constrain, because we have a lot of parameters here. Okay, so we use this M squared, like the capital M, to fix the amplitude of the CMB. So this basically gives you the energy of the inflation. So you can always choose M to really fit the amplitude of the CMB. So this is fixed for us. So we're not going to deal with M like a free parameter, because we're guaranteeing the amplitude of the CMB with this parameter. And we did analysis with the whole thing, changing all the parameters. And you can see that these two are the most important one, the chi naught and D. Okay, so what they do, These are one of the spectra. So this is scalar spectra. So it's very small, but I'm changing D here. Okay. So I'm decreasing D from red to blue. I'm decreasing. And what you see is shift a little bit the position of the peak, but mostly increase the peak. Okay. So every time you look D, you can imagine that you're changing the amplitude of the peak. Okay. Chi naught is different. Chi naught doesn't change the amplitude, but shifts a lot the position of the peak, right? So, and I'm varying chi naught. It's increasing from blue to yellow. So when you increase chi naught, you see that you have a huge shift in you broaden a lot your spectrum. Okay, so when you look to chi naught, you think I'm moving the position of the peak. D, you are amplifying or lowering the peak. Okay, just that's the thing that I have to remember. There's so many things to talk about this. Okay, I'm aware. Okay, so we did. Okay, so you have to control when the system crossed the horizon, every scale that you want to test. So we did for, okay, so the most important scale is the CMB, of course. So KCMB is fixed, but we are using the Planck fiducial scale. And you can show that this delta N CMB, what is delta N CMB? So you have, during inflation, you have when the KCMB mode crossed the horizon till the end of inflation, okay? That's what we're calling delta N CMB, okay? So it's how many E-folds you have between crossing the horizon, the CMB crossing the horizon till the end of inflation. And you can rewrite this in this kind of formula. This V here is the potential when you cross the horizon. So you have kind of a NCMB here inside also. So we have to solve this iteratively, right? You cannot like just plug the numbers. You have to solve it like doing iterations. And this is the duration of reheating. One of the things that we learn in this study is that the duration of the heating has a huge impact on constraining the model. And we are like describing reheating here in a very phenomenological manner. We are not doing like microphysics reheating. So I think that going to like deeper in reheating will be very important in the future. But okay, so you can write in this way, and we are ending the reheating at before 1 TeV. So we wanted to be safe in the standard model. Like we don't want to mess up with baryogenesis and big bang nucleosynthesis, anything. So to be safe, we impose that we have a maximum duration of reheating, meaning that reheating must end before 1 TeV, okay? So, and you see that here comes with a minus sign. So the maximum number of delta and CMB is when you have like an instant reheating, like the duration is 0, right? So instant reheating is when this quantity is maximum mass, okay? And we can calculate, okay, so there's the maximum value of delta and CMB, and there's the lowest. The lowest is when you have the maximum number of reheating, right? So you have a range for delta and CMB, okay? So we look for, so we have the whole around space, you go for each point, you evolve the system, and we see that we can have like delta and CMB 50, 52.5, and 54 for all the models we have there, all the points in Berman space. And you can calculate how much reheating each one of these can have. And the important point here is to see that the lowest delta and CMB is when you have the highest reheating, right? So when you look for delta and CMB 50, remember, it's a lot of reheating. And increase this guy, meaning decreasing the duration of reheating.
So what is this parameter W?
I'm sorry. Oh, droga. Here.
Yes.
This is the effective equation of state during reheating. So this depends on the potential you have. So the inflaton, it's oscillating in the minimum of the potential. So it will give like kind of effective fluid. And for us, it's just dust.
This is phenomenological model for
Yeah, this is just like making like N is the log of A, so you like keep doing like fractions and you can write this in this way. It's kind of logic. Okay, so now we have some control of crossing the horizon, so we can constrain large scale structure. So you use the Planck data. We don't run MCMC or whatever. We take the best fit and see if our model is within or outside the best fit, and that's it. Okay, so it's the first and maybe the easiest and very yeah, so simple thing to do. So we have this kind of parameterization. So I have the amplitude. This is easy. We fix with the m squared. So we have the spectral index and a possible running. So we are looking for a lambda CDM plus R plus alpha. And we have, so we can calculate these guys. We have the scalar spectrum. So we can really calculate these guys with the evolution of the system. Okay. So we calculate this numerically. And you use this range of data to calculate. Okay, there's some choices here that we should discuss afterwards, but that's how we do. Okay. Okay, and we get this kind of constraints. So chi naught is the position of the peak. D is the amplitude, right? And this blue region is excluded due to the spectral index. There's also a blue region here, and there's this yellow region excluded due to running. Okay, so running is very constraining. Actually, it's very barely larger, but some of the points here are excluded just because of running, not because of the spectral index. This was not obvious at first. And we really can understand this. It's not that difficult. These really high chi naught are excluded because you're moving too close to the CMB that is here, right? So you're already destroying everything, you're spoiling everything of the CMB. It's not that difficult to understand why above this chi naught you have you are constrained. And this region, it's constrained because even though the bump is very far away from the CMB, you're too red here. So you can check that this gives a too red spectrum.
So what are the constraints on alpha x? I cannot see from this plot.
Oh, it's the Planck. I'm using this. You use the Planck best fit and constraint to exclude the.
Okay. So alpha x is the running of the running. Okay.
Yeah.
And alpha of the model, do you have a constraint on alpha of the model?
Oh, the parameter of the
Yeah,
model.
yeah.
No, you mean the?
Yes.
No, alpha is fixed to 1.
Alpha is fixed.
Yeah, we have too many parameters, so we are working only with these 2. All the others are fixed, like freezing. We did analysis with everybody open, but we didn't see anything very important, and was a mess to write a paper with all the 6 parameters open. It was, so we fixed 2 and. Okay, so this is for delta MCB 50, and you can do for different duration of inflation. And again, this is shorter reheating, and you see that going to longer reheating, you exclude much more points, okay? So the duration of reheating is very important to constrain your model. That's the first take-home message here. And we plot also this is the LISA, if you're the peak of the power spectrum, the peak of the power spectrum, this is the LISA scale. So this region, LISA won't see anything because it's excluded because of a large scale, but maybe here you can have a LISA checking this thing. I will go into that. And you have also PTA here, right? Okay.
You're saying that PTA doesn't add anything.
Won't be able to see this right off the bonds, yeah, because it's excluded for large scale structure first. Yeah. And we checked for ICE telescope also.
And
No, you can see. Okay. Yeah, it's too far away from. But yeah, well, I'll get into gravitational. This is just a constraint. I'll probably move faster. So we checked the mu constraint also. And mu constraint is a different thing. So here the constraining. So this is the limit, and you can constrain the parameter space also, and you can put everything together. And it's nice to see that mu constraint can is more constraining than the logical structure also. So another take home message here is that never ignore mu constraining. Okay, so you really have to do all the constraining, otherwise you are not properly constraining your model.
Because the slides, I was going to ask you how it fix the minimum value of key link for one megahertz. What was the prescription?
Oh, I don't remember. You remember this? Why K minimum is 1 megapascal inverse? Remember?
Yeah, I don't remember that today,
Yeah.
but in the end, like, it doesn't matter because this window function is like, it
Yeah.
starts from.
It doesn't change much, but
Yeah.
yeah, I can look into the paper and give us the reference.
In the regarding window function, was there a reason for it?
Yeah, yeah, for sure.
What was that saturation?
I can explain you later. But this is you have to really go into the view distortion, how it works and all that. That I can give you some papers both. Okay, so you put everything together and you have this white region that is the allowed region, parameter space region that are safe for large scale structure. Okay, and we check non-Gaussianity also. I'm going very fast on this because, yeah. So there's a lot of things to look here. Gonzalo said yesterday, so you have different shapes. You have like equilateral, squeeze, folded, isosceles. And you can, so you have the FNL, the generic bispectrum here. And you can parameterize all this, looking for this KT, that is the sum of the three Ks, and we find this alpha and beta, right? So changing the alpha and beta, you go from one configuration to the other. Here are some examples. So folded is alpha equals 0, beta equals 0. Equilateral is alpha equals 0, beta 1/3, and so forth. Okay. So for one specific point in parameter space, let's say this one, you can run the simulation. You have the scalar spectra here, and you can calculate the FNL. Okay, and we did for 4 different configurations here. So the CMB is here, so you see that FNL is very small, so it doesn't put extra constraints on your model for this model at least. So all the shapes are safe concerning Planck constraints, and you see that here that is basically in the peak region. The FNL is flat and it's independent of the configuration. Okay, and actually you can check, and the FNL that we get numerically is very similar to Maldaceno's consistency relation. I don't know what goes here with. I have to talk with Gonzalo to understand better if this is correct or not, due to the gauge issue. But I'll see later. So this it's suggesting us that this model has only local non-Gaussianities. Okay, and so these are for just 4 configurations. Now you can do the same thing, but vary alpha and beta for all alpha and beta possibles, and you see this kind of plot. So for all alpha and betas, and you see that mostly FNL is really constant, right? So you can be really confident that you have like a local non-Gaussianity, okay? And all are very small, so you're not going to put extra constraints on the CMB or on your model. Yeah. So just a last few words on the Gaussianity. The Gaussianity is very small, and we don't have to worry about loop corrections when you calculate primordial black holes. Okay, so I can come back to this at the end. But since everything is very small, we can do primordial black holes and scalar gravitational wave without worrying too much about the non-Gaussianity of this model. Okay, that's the point here. Okay, so to finish small scale phenomenology, so you can calculate primordial black holes. So this colored region are the allowed region considering the large scale constraints. And this black hashed region, it's excluded due to overproducing primordial black holes. Okay, so even though large scale structure constraints allow all these region of parameter space, everything above this line has to be excluded because you're overproducing primordial black holes. So it's very constraining, and we understand this as kind of a theoretical test, okay, because we don't have a measure of. Okay, and below this dashed line is not interest from the primordial black holes point of view, because you basically don't produce enough. So you won't have any primordial black holes here. So this small strip here is the interesting region for primordial black holes.
What is the typical mass of this primordial black?
No, we didn't calculate that. Something that we had to finish the paper, like 2 years working on this. So, but yeah, it's a very good question. We wanted to calculate this.
But this wasn't this derivation in the mass plot? No.
Sorry?
So wasn't this derivation in the mass plot for the primordial black hole?
Oh, for this model? Yeah, I don't know. That's
No,
what.
no. Yeah, but I thought that this was a relation in the plot of the mass
In the beginning,
in previous slides, but maybe.
for the mass of the primordial black holes and
Yeah,
with.
there were two windows.
Yeah, that's something different, not for this model. That's like constraining from all different kind of experiments. So, and I didn't calculate the mass of this, so I cannot like see how this translates in that plot. That's something that we need to do. Okay. And okay, and you can check how this varies with the number of the duration of reheating also. And you see that also the duration of reheating here impacted the final result. Yes, so it's very constrained. Okay. And finally, scaling this gravitational wave. So we also calculate the scaling this gravitational wave, how much gravitational wave you can produce with this kind of models. And so this red with dots, red dots are excluded, not excluded, sorry. So what is this? This region here is not interest for us because you get a signal that's below the signal to noise ratio from astrophysical sources. Okay, so you calculate the signal to noise ratio from these models, and you have to compare with what is the foreground sources. And this region here, you get a signal, but it's below the foreground. So it's not interesting for the model. You won't be able to measure anything. But it still survives a small strip here that has all the nice features. Okay, so it passed from large scale structure. It's okay with primordial black holes, and possibly can be measured by LISA. Einstein telescope, everything is excluded. It happens something like this. Okay, so if you change the number of reheating, you go from here to here, and you see here that for delta and 50, that's the longer reheating, you'll be completely dominated by noise. Okay, so so understanding and controlling what happens during reheating is crucial to see if you'll be able or not to measure anything in future surveys. That's one of the things that we're learning in this analysis. Okay. Okay, so that's it. Basically, early universe is a testable arena nowadays. There's a lot of things, nice things to do. You have to check everything to be consistent. It's very demanding, but that's how it is. And yeah, so nice. There are a lot of nice things to do in the future. Okay, thanks.